So we've got ourselves a little bit of a menu for factorising polynomials. We know that we can use the remainder theorem just using trial and error to find the zeros. And when we do that, we're effectively saying what is p of 1, -1, 2, -2. We try a variety of numbers, and what we're looking for is that p of something needs to equal 0 for that something to be one of the zeros of the function. And we can then use the 0 to work out what the factors are. Once we've got a few factors, we've learnt that we can use long division to find the rest of the zeros or the rest of the factors. If we know one, we know the other. But we always want to look for tips that will help us get things done more quickly and easily. So it's important to know when to throw your effort after finding the zeros with this method and when to just call it quits and use your long division. So here's a tip. If you know that a certain polynomial has a certain number of distinct zeros. Now, let's just pause there. How would we know how many zeros it has? Well, let's think. A diagonal line is only going to have 1 0. Degree 1, 1 0. A parabola, it can have no zeros at all, or it can have 1 double zero, but it can have 2. So the degree is 2, it has a maximum of 2 zeros. A cubic will have a maximum of 3 zeros. So we can look at the degree and reason how many zeros it might have, but it could also have less than that number that is the degree. But if we actually know how many distinct zeros a polynomial has, and we might know it because we've been given a graph and perhaps it's labelled just with alpha, beta, etc., for the zeros, and we've got to find those values, or perhaps we've been told that a polynomial has 4 distinct zeros, find them. Well, if we know how many we're looking for, then it gives us some clues as to how long we should persist with this method and when we might need to call it quits and use this method. So if we know how many zeros there are and we know the leading coefficient and the degree, it might be quickest actually to stick with this top method and find all of the zeros using the remainder theorem. But we want to make smart choices. So far we've just been trying 1, -1, 2, -2 and sort of going along our numbers like that. But if all the coefficients are integers, and I don't just mean the leading coefficient now, I mean all the coefficients of all of the terms of the polynomial, if they're all whole numbers, then all of the integer zeros, all the whole number zeros, will actually be factors of the constant. And we haven't really paused to consider this before. I mean, it seems kind of obvious once you notice it. But this is going to help us a lot because we can make much better choices now with our trial and error. Now, if you don't know how many zeros there are, be prepared to use long division because you might be looking for something that's literally just not there. So then if we know that, say, alpha 1, alpha 2, all the way up to alpha n are distinct zeros of some polynomial, then we can always arrange it in this form. And we've done this already quite a bit with quadratics and with cubic curves and with some quartics. But the really important thing to note here is the leading coefficient, a, which needs to sit out the front when you're doing your working here. Then it's a matter of finding all of the factors, and if you know the zeros, you can work out the factors or vice versa. So let's have a look at how this works in an example. I've got here a monic polynomial, and that's important because I can see there that the value of a is 1. So as I go to think about what this factorisation is going to look like, and I've got this kind of arrangement in my head, I can see that the a out the front is just 1, so I don't really need to even write it. So now the next clue to look for is the fact that I've got -30 there as the constant. So that means that when I multiply all the lasts out of each of these sets of brackets, what I'm going to get is -30. So there's no point trying anything that is not a factor of -30, especially given that I've got a monic polynomial here. So we're going to start the usual way. Let's put something into our calculator to be a. So let's start with 1, shift store a, put it in. Now I need to write this formula in. So I've gone ahead and put in the formula using my red a anywhere that there was an x, and because I've already put in a value of a being 1 before I started, when I hit the equals button, I got 0 straight away. So that tells me that 1 is a 0, which means that x minus 1 must be a factor. Now, I haven't put anything here for the leading coefficient because I've reasoned that it's a monic polynomial, so the value of a there is 1, which means I don't really even need to write it. Now, I've got my clue over here. I can see that there's 4 distinct zeros here, and it's got a degree of 4, so there couldn't be more than 4. There might be less, but I can see that there's 4. So I know that there's a 1 here. I know I've got distinct zeros. I can pretty well go ahead and see what the shape of my answer is going to be. The next thing I can reason is that all of these numbers multiplied together, the lasts of each set of brackets, is going to multiply together to make negative 30. Now, I've already got negative 1. That means that these three need to multiply together to make 30. So we're going to begin with our usual trial and error. We'll try 1, minus 1, 2, minus 2, whatever, as long as they're factors of the number. But then our choices get narrowed down really quite quickly, and that saves us a lot of time. So now let's try negative 1. Shift store A, up button equals. Nope, that's not a factor. Try 2. Nope, that's quite quick and easy to do. Negative 2, we'll try that. And yes, negative 2 is a 0. So if negative 2 is the 0, then the factor is x plus 2. Okay, so I'm narrowing it down now. I've got negative 2 so far. That means that when these two are multiplied together, they must multiply to make 15, because 15 times negative 2 will give me my negative 30 as my constant term. So to get 15, I'm thinking it needs to be either 3 and 5 here, or negative 3 and negative 5. Now I'm working backwards. When I was putting numbers into my calculator, I was looking for the 0 and then using that to generate the factor. Now I can actually think about what the factor might be and check it. So I'm not really using trial and error, I'm sort of confirming a suspicion. So let's try 3. It's either going to be 3 or negative 3, and that will tell us what the other one is. We'll put 3 in. And it's not 3. That pretty much tells me it must be negative 3. And if negative 3 is the 0, then x plus 3 must be the factor. Let's double check it. Negative 3, make that a, up equals, yeah, sure enough. And so now I can pretty much automatically put in a 5 there, because I can see that I need that to multiply to get my last term. To confirm that x plus 5 is a factor, I need to just check that negative 5 is a 0. So put your negative 5 in, up button equals, yep, sure enough. So I can pretty well confirm that I'm right now. I've got the right number of zeros for my picture. I've got the correct constant term and the correct leading coefficient. So I'm pretty confident that the rest is all just going to work out nicely. And then a final check with this question is that we seem to have 3 negative zeros and 1 positive 0. And sure enough, our zeros would be positive 1, negative 2, negative 3, and negative 5. So it looks right. In this example, we're told that this polynomial has 4 distinct zeros. And then we need to graph it. So we need to find out what those zeros are. So first step, let's put in our leading coefficient, which we can see is 2. Put that out the front, and then reason that we're likely to have 4 distinct zeros there. Now, as we go to find them, we're bearing in mind that we need our constant term to be 20. We're already starting with a 2 out the front. And that means that each of these 4 sections here are going to have last terms that multiply together to make 10. Now, 10 doesn't have that many factors, so I'm thinking that a 1 and a minus 1 are really likely things to have. So same strategy as before, let's put this polynomial expression into our calculator using the red A. If you've already got one in there, then an easy hack is to actually just go back to your previous expression and change it so it looks like the new one. Okay, so I've got my formula ready to go. It'll already have a value of A in there, so I'll hit equals, but then I can't remember what value of A I used last time. So put in 1 to start with, and up till you get to your formula, and equals. And sure enough, I've found that P of 1 is equal to 0. So that means that x minus 1 is a factor. Now remember that the 2 multiplied by all 4 of these numbers needs to make 20. So I've already got negative 2. That means that the last 3 numbers here need to multiply to make negative 10. So I'm thinking 1, 2, and 5 are the likely digits that I need, but I'm not sure if they're going to be plus or minus. So that narrows down my work considerably. So let's put in negative 1 now, see if that's a 0, and it is. So that gives me x plus 1 as a factor, because P of negative 1 was 0. This is not a bad way to just keep track of what you've done. Now I've got negative 2, and I'm looking for 20, so these need to multiply to make negative 10. So now let's try 2, see if that's a 0. And it's not. That means I'm almost certain that negative 2 will be. So just to confirm, yes it is. So if negative 2 is a 0, then that means that x plus 2 is a factor. Now I can pretty easily reason here what this number needs to be, because I've got 2, negative 2, negative 2, negative 4. This must be a negative 5. So now I can go ahead and graph this thing really easily. I've got zeros at 1, -1, -2, and at 5. And I know that it's a quartic curve, so it's got something of a sort of W shape. None of these are doubles or triple zeros, they're all just single ones. So it goes something like that. And I know that this is not very well to scale actually because it goes through 20 on the y-axis. So let's make it go way up more like that and call that 20. And that's a reasonable enough sketch for what I have.